Let's talk about the invisible world all around us, the world of molecules. Today, we're going to explore two incredible tools that scientists use to identify pretty much any substance with amazing precision just by watching how it wiggles. So, how in the world do you identify something you can't even see? Well, imagine you could tell the difference between a guitar and a violin just by the sound they make. It's kind of like that. You see, molecules aren't just sitting still. They're constantly moving, constantly vibrating at their own unique frequencies, almost like they're humming a little tune that only special instruments can hear. And that idea is at the heart of what we call vibrational spectroscopy. The key concept here is that every molecule has a unique vibrational fingerprint. It's totally unique to that molecule. So if we can measure that fingerprint, we can figure out exactly what we're looking at.
So what does that mean in practice? Well, it's pretty simple, really. We shine a form of light, or radiation, onto a sample and we watch what happens. The molecules in the sample will only interact with the light if the energy of that light perfectly matches the energy of their own natural vibrations. So, by seeing what energy gets absorbed or scattered, we can map out that fingerprint, piece by piece.
You see, the bonds holding a molecule together aren't rigid little sticks. You should think of them more like tiny springs. And just like springs, they can stretch and compress, they can bend, they can even twist and rock around. All of these different movements happen at very specific energy levels, and that's exactly what we're trying to measure. And it gets pretty detailed. As you can see here, there's a whole catalog of these vibrational modes. You've got atoms stretching apart and then coming back together, either perfectly in sync or moving in opposite directions. And then you have these more complex bending motions, with fun names like scissoring, rocking, wagging, and twisting. It's like every molecule has its own tiny, perfectly choreographed little dance routine.
Okay, so let's meet our first tool for watching this dance. This one's called infrared, or just IR, spectroscopy. If there's one word you need to remember for IR, it's absorption. IR works by figuring out which exact frequencies of infrared light a molecule decides to soak up. But here's a little catch. IR can't see every single vibration. It only pays attention to the ones that are IR active. And what does that mean? Well, it means the molecule's overall electrical balance, what scientists call its dipole moment, has to change while it's vibrating. Basically, the vibration has to cause a little wobble in the molecule's electrical charge for the infrared light to notice it. And the instrument that does this, the IR spectrometer, is actually beautifully straightforward. I mean, look at this path. First, you have a light source that creates a whole beam of different infrared frequencies. That beam then passes directly through your sample. As it goes through, the sample absorbs only the frequencies that match its vibrations. Then, a detector on the other side simply measures what's left. The frequencies that are missing, well, that's your fingerprint. But think about this for a second. How do you even hold the sample? You can't just put it in a glass container, because glass actually absorbs infrared light itself. So scientists have to use these special windows made from materials that are transparent to IR. A really common one is made of sodium chloride. Yep, basically a crystal clear plate of salt. But you have to be careful. If your sample has any water in it, that salt plate is just going to dissolve. So choosing the right window is a really crucial part of the experiment. All right, on to our second tool, Raman spectroscopy. Now, if IR was all about absorption, Raman is a whole different ballgame. It's based on a completely different phenomenon called scattering. Instead of looking for the light that gets soaked up, we're looking at the light that bounces off the molecule. And that gives us a totally different, but just as powerful point of view.
And, you guessed it, Raman has its own rule too. A vibration is Raman active only if it causes a change in the molecule's polarizability. That sounds complicated, but it's basically a measure of how squishy the molecule's electron cloud is. So, for Raman to see a vibration, the squishiness of the molecule has to change as it moves. Now, the Raman spectrometer is a bit more of a beast, instrument-wise. It all starts with a very powerful, single-color laser that gets blasted at the sample. Now, almost all of that light, we're talking over 99.9%, just bounces off with the exact same energy. That's called Rayleigh scattering, and we have to get rid of it. The real magic is in the tiny, tiny fraction of light that scatters back with a slightly different energy. That's our Raman signal. The absolute biggest challenge in building one of these is the filter. You need something that can block the ridiculously bright laser light while letting that incredibly faint Raman signal sneak through to a super sensitive detector. It's a real engineering feat.
So, you might be wondering, we have two different techniques that are both measuring molecular vibrations, just in different ways. Why do we need both?
Why not just pick one? Well, when you put them side by side, you start to see why they're such an amazing duo.
And this table really shows you their incredible synergy. You see, IR is amazing at seeing polar bonds. Those are bonds that have a clear positive and negative end, like the OH bond in water. Raman, on the other hand, is a rock star when it comes to symmetric, nonpolar bonds, like the carbon-carbon bonds that make up the backbone of so many molecules. But that last point, that's the real game changer. Water is a total nightmare for IR because it absorbs so strongly. But for Raman, water is practically invisible. This is huge. It means scientists can study biological samples, like living cells, in their natural watery state.
This quote just sums it up perfectly. What it's really saying is that these two techniques are like two sides of the same coin. A vibration that's screamingly obvious in a Raman spectrum might be completely invisible to IR, and the other way around is true too. They don't compete with each other, they complete the picture.
Okay, so this is way more than just some cool science for a lab. These instruments are absolute workhorses out in the real world, solving some really fascinating and important problems every single day. For example, an art historian can point a Raman microscope at a 1,000-year-old manuscript and tell you exactly which minerals were used to make the blue pigment, all without damaging it in the slightest. Or a forensic scientist can analyze a microscopic fiber from a crime scene to help solve a case. It's pretty amazing.
And in industry and healthcare, the impact is massive. These tools are used for quality control, making sure the plastics in our phones and cars are made right. They're developing ways to spot fake medicine without even opening the box. And in hospitals, they can even be used to monitor the gases a patient is breathing in real time during surgery, which is absolutely critical for safety. So whether it's by looking at the light that gets absorbed or the light that gets scattered, IR and Raman spectroscopy give us these two incredible complementary windows into the invisible dance of molecules. They are fundamental tools for everything from preserving history to creating the future of medicine. And as the instruments themselves get smaller, faster, and even smarter, you just have to wonder, what other molecular secrets are they going to help us uncover next?